Well, I'm sorry to use blackboard, but because I'm very old, I may be old-fashioned also. And, well, je voudrais continuer la bonne tradition. D'abord, féliciter les deux nouveaux-nés. Bon anniversaire. Happy birthday. On the language which sounded around the cradle, с днем рождения. And now I again follow the tradition and pass to the mathematics. The problem which I'm interested in looks as follows. You have an observation x. This observation takes its value in some measurable space xa. And have probability distribution p theta, where parameter theta belongs to some parametric set theta. So we observe x, the family p theta is known, the set theta is known, but the value of the parameter theta is unknown. What we would like to do, to use the observation to estimate the value f of theta of a known function f in unknown point theta. In fact, I will not, of course, consider such. It's a very general problem, and it includes almost all estimation problems. For example, the problem of parameter estimation, you will have an f of theta is just theta. And semi-parametric models also are included into this scheme. So it's very, very general scheme. And in fact, of course, I will not consider the general problem. I will consider only three following scheme of observation. The first, we observe x epsilon. It is a random function such that dx epsilon of t is s t theta dt. Or more the same, but like this. In both these cases, t belongs to the interval 0, 1. The third scheme, the same. And now t belongs to the real line. And the fourth, just classic scheme of IID observation. An unknown parameter theta of t, theta of x, density function of well, about parametric set, we may consider two different suggestions. The first, theta is finite dimensional, or theta cannot be embedded into finite dimensional space. The first case I call parametric, and the second case I call non-parametric. In parametric case, the problem which I would like to consider, is not very interesting. Everything can be reduced to the estimation of parameter. Well, let's consider, for example, the first observation. Well, under white condition, you may prove that maximum likelihood estimator will be asymptotically efficient, and if theta epsilon is the maximum likelihood estimator for theta in the problem 1 with finite dimensional theta, for example, then theta epsilon is asymptotically efficient, asymptotically normal with some information matrix I of theta, and then we may take as estimation of f of theta, just plug in estimator. F hat epsilon is f theta epsilon hat. And it's very easy to see that f epsilon minus f theta anyway for function f with bounded derivative will be f prime theta epsilon minus theta and plus or small. Well, and because theta hat minus theta has asymptotically normal distribution, then it's very easy to see that with my expectation of f epsilon minus f of theta square will be asymptotically epsilon square and norm of f prime theta. Sorry, of course not. Of course not. It will be, of course, trace f prime and information matrix. I forgot about it. It's not always identity matrix. And again f prime. So the rate of convergence is always parametric and absolutely no problem. And the situation drastically changes if theta is infinite dimensional. In this case, everything will look very, very different. Well, so let's deal with observation scheme 2. And so suppose that unknown parameter theta belongs to some subset theta of L2 function. So now theta is infinite dimensional and it is subspace of subset of Hilbert space. And then we'll see that the behavior of our estimates will depend on the structure of the set theta and from the behavior of our function we would like to estimate. Well, let's consider two very simple examples. Example A. Suppose that we would like to suppose that theta is a unit ball in L2. And the function f theta we would like to estimate is linear. F is known, so L is known. So, in this case, there are no consistent estimates of theta because the ball is too rich set. But in the same way, we can estimate we can find effective efficient estimates for f of theta, very simple. They estimate f hat, which is 0, 1, a of t, d x epsilon of t is f. Is unbiased and normal, not asymptotically, just normal, and it's very well behavior of the variance. So we cannot estimate the parameter theta, but we can efficiently estimate the value f of theta in the case of linear functions. In the same way, a little bit more complicated function b cannot be estimated even consistently, even if theta is not whole ball but only the point 0 and the surface of the ball. In this case, f of theta takes only two values, 0 or 1, but there are no consistent estimates. To have consistent estimates of such function, you need to put some extra condition on theta. It should be not so rich as a whole unit ball. And what really will happen? I formulate in the following theorem, which was in some sense the beginning of this theory. So we began to study this problem, to understand what is the connection between the functions and properties of theta, with Kosminski somewhere in the end of 70s. And one of the first results look like follows. So suppose that we have suppose that we consider this problem 2, and suppose that theta has the following property. Kolmogorov diameter dn of theta goes to 0 as some power of n. I remind you that Kolmogorov's diameter or Kolmogorov width, it is a minimal distance Mn run all n-dimensional linear manifolds, and so it is the rate of approximation of theta by finite dimensional manifolds of dimension n. So you see there is some kind of connection between this notion and between the notion of approximation theory. For example, when you approximate by polynomial of degree n, you have some estimation of Kolmogorov diameters. So that's, I remind you, and it was the first condition. The second condition was on the functional. So we have supposed that the functional f of theta is differentiable and its derivative, it's Freche derivatives, satisfies Hölder condition, namely norm f prime h2 minus f prime h1 less than some constant m norm h1 minus h2 in some power gamma. And then we have proved that if if between beta and gamma there is such connection to beta gamma greater than 1, then asymptotically efficient estimate of f exists. Later, Arkady Nemirovsky joined to us, and we have spread the theorem on the case when we have not one derivative but k derivative, and we have found the relation between the rate of Kolmogorov diameter and the smoothness of the last derivative. And later, Nemirovsky showed that all these relations, like this one, are precise. So if, for example, it's possible to find such examples when this relation is not fulfilled and there are no asymptotically efficient estimates. About all these things, well, you can read it, very good exposition written by Nemirovsky in lecture notes in math. Well, it seems to me it is a number. I'm not absolutely sure. So we have rather good theory for this case, and we also have proved more or less the same result as I formulated before for the case of IID observations. Well, it looks nice, but not absolutely. What will happen? Well, for example, consider this case. The theory looks very well when density theta of x is a compact support. But if the density theta x, if the support of density theta of x is whole real line, our theory does not work, just because all more or less interesting classes of functions defined on the whole real line will have Kolmogorov diameters which are not go to 0 and goes to 0. You cannot approximate really interesting functional spaces by finite dimensional subspaces. Well, I just give you some simple example. So from now, I will consider only the problem 3. And I would like to show you at first that in some very interesting cases, Kolmogorov diameters dn of theta will not go to 0. So now I deal with the set theta, which is subset of L2 R1. And consider the class of very, very smooth functions. Consider the subset theta t of such function theta, the Fourier transform is 0 when t is outside of interval minus tt. It's a very narrow class. In fact, it follows from Pauli-Wiener theorem that the class the t consists of the integral analytic function of exponential growth. That's very, very, very smooth function and so on. But it's very easy to see that all Kolmogorov diameters will be greater than some constant n which is bigger than 0. To show it just enough to notice that all the functions of the type sine t they all belong to this subspace, and for such and you have an infinite number of such functions which are orthogonal, so the some unit ball will belong to theta t, infinite dimensional unit ball, but all Kolmogorov diameters of unit ball are 1. So the theory will not work in this case. In fact, it's phenomenon well known in the approximation theory. You know that continuous function on the closed interval can be approximated by polynomials. That's classical Weierstrass theory, but you cannot approximate function of the whole real line by polynomials. And you need some different approximation theory for functions defined on whole real line. I think the beginning of this theory goes back to Bernstein, who also worked in probability theory. You know, of course, his works. Well, so we need to change a little bit the type of our problem. And I change it in such way. We will consider the following generalization of Kolmogorov diameter. To define this generalization, I need the notion of reproducing Hilbert space. Reproducing kernel space. So reproducing kernel Hilbert space is the following thing. H is Hilbert space of functions theta of x, where x takes its value in some space x, with scalar products theta 1, theta 2, and which satisfy the following property. There exists a function k of xy such that for any yk, y is element of H, and scalar products k y theta is theta y. For example, the space of this space is reproducing kernel space in L2 with the kernel kxy, which is equal to 1 divided by sine t x minus y, x minus y. And my generalization of Kolmogorov diameter will look as follows. Rt theta is and now is taken over all subspace MT which have a reproducing kernel, and reproducing kernel is bounded by the number t. So we take so the space reproducing kernel, and this reproducing kernel kxy is bounded by t. For example, this kernel is bounded by t. It's okay. You may consider as approximating spaces the spaces of integer functions, but maybe some other also. And then the result, which I would like to present here, looks like this. It looks just as our result is Kosminski, but instead of the n theta here, we put this expression rt theta and just the same demand. The second condition is just the same. The function f should be differentiable and the derivative satisfies Gildar condition, and the condition on beta and gamma again is the same. So under this condition, efficient estimates of f theta in the case of problem 3 exists. Well, so I have absolutely no time, of course, to discuss the proof, but just only a few words to explain you why it will work. Suppose that we know, in the case of problem 3, suppose that we know that theta is just some subspace HT with reproducing kernel K. In this case, we may consider the following estimate for theta. Integral minus infinity infinity K Ts dx epsilon s, which is integral minus infinity infinity K Ts theta of s ds and plus but the first integral, because K is reproducing kernel, is just theta of t. So the estimate is unbiased, and you see that because KTS is bounded, that the variance is of order epsilon square t. So the space theta is infinite dimensional. Nevertheless, you can find the estimate of theta with parametric rate of convergence. And now, now to prove the main theorem, you have to approximate the space theta with reproducing kernel spaces, and to continue all this machinery. And, well, so I think that's all.